All right, back by popular demand, today we're doing another LeetCode session. As always, I have not prepared these questions in advance. I'm just picking them blindly and doing them in real time, talking you through my thought process. All right, let's get into it. Let's start with the daily question. Given a binary string s without leading zeros, return true if s contains at most one contiguous segment of ones, otherwise return false. Okay, so we have a 1, and then we have another 1. Well, I feel like this is pretty straightforward. Again, of course, easy question. So we would go through, we would find the first 1, keep going until we find another 0. Then the counter starts in that if we find another 1 before the end, we return false. Otherwise, we return true. But if we never find a 1 in the first place, we also return true because it says at most one contiguous segment of 1. Oh, but we don't have leading zeros, so the first one will always be 1. Will we ever have an empty string? Let's think about edge cases here. So S0 is 1. The length is at least 1. So if the length is 1, obviously true. Okay, that simplifies it a little bit. So we go until we find the first 0, and then we go and see if we can find another 1 after that 0. Let's write this out in English before we do any code. Go until we find 0 or the end. If end, return true, obviously. And then if end, return true. We went on a little bit of autopilot there. Okay, if end, return true. If 0, set a flag, and then go to end. If finding any 1, return false. If get to end, return true. Not sure if we'll need to set a flag there. This seems like a pretty straightforward question. Okay, so we'll just say for I in string. Yeah, well, let's go for a flag. Flag is, let's say, what should we name this flag? Well, what does it represent? We're representing, are we looking for 1s? Right. This is Python. Okay, are we looking for 1? No. For I in string, if we're looking for 1, then if I is 1, turn false. But if we're not looking for the 1, then we want to make sure it's a 0. So if it is 1, everything will be 1 up until we find a 0, then we're going to say looking for 1 is true. And then if we get through the entire thing, if end return true or if end return true, so that means once we're done and we haven't returned false, we return true. Let's see. Is it really that simple? For I and S. Yes, our string is named S. Perfect. Okay. All right, let's go. That was pretty easy. I mean, it is an easy question. All right, next one. Let's do another one. What is it? Random question? Like that? Find and replace pattern. Given a list of words and a string pattern, return a list of words that match pattern. You can return the list in any order. A word matches the pattern if there exists a permutation of letters P so that after replacing each letter X in the pattern with PX, we get the desired word. Okay, what? Let me look at the example because this is not clicking. Okay. ABB. Oh, okay. So ABB, MEB, AQQ. Oh, okay. List of words, match pattern. Yeah, so can we map each letter to each other letter? Or like, does there exist a map like this from the pattern to the word? So what would be a brute force solution? Okay, I think here my comment template might help us out. So what are my first thoughts? So a brute force solution would be to go in and, well, first off, are the words in the pattern always going to be the same? Yes. Or the same length? Yes, they are. So we could start going in and, okay, A goes with A. We don't need to replace anything. B goes with B. I don't need to replace anything. C goes with B, and then we replace C with no. because that wouldn't work. So we cannot map two letters to the same letter. Let me think about this. So, okay, my first intuition is kind of, can we convert both the pattern and the words into some sort of generic pattern? I think we can. So, okay, what I'm thinking is instead of the letters, we have first letter that occurs, second letter that occurs. So, for example, in this word, the first letter that occurs is M. We replace that with 0 indexed. And the second letter that occurs is E, so 1, 1. So this would be 0, 1, 1, right? Also 0, 1, 1. And then the pattern, first letter that occurs is A, 0. B is 1, 0, 1, 1. So we can pre-process it that way. In terms of time complexity, we would have to pre-process every word, so O of n, and then we'd have to check every word against the pattern. So that's another O of n, so that's 2n, so still O of n. Is there a way to do this without pre-processing? To only need one pass through instead of two? You know what? I like my pre-processing approach. I'm just going to go ahead and implement that. So we're thinking this would be O of n time, because we would need to go through it twice, but just twice. And then it would need O of n space complexity, because we would need to make another list of words. And then for the output, the new list will be the same indexes as the old list, so we can just look up the old list again. How do we solve this? Let's write out our approach in English. So we first pre-process the words and pattern to have first occurrence. It's making me think. So how are we going to actually pre-process this? This is where I'm thinking we might not need it to go to numbers and back. So obviously, when we're pre-processing, we're going to say, okay, have we seen A before? No. A is 0. We'll have to make a dictionary then. All right, have we seen B before? No. B is 1. Have we seen C before? No, C is 2. Now let's say, have we seen M before? No, M is 0. Have we seen E before? No, E is 1. Have we seen E before? Is it in the dictionary? Pre-process the words and pattern by replacing letters with their occurrence order. Then we simply check the word against the pattern, and if they match exactly, they match. If they don't match exactly, they don't match. Compare each word with pattern exactly. So how do we pre-process the words? Let's think about that a little bit more in depth. I mean, we already did, but let's just write it out. So dictionary mapping of each word, of each letter. So seen letters get looked up, and unseen new letters get added as length of the dictionary plus 1. No, length of the dictionary. If the dictionary has nothing, it's 0. If it has 1, it's 1 because it's 0 indexed. Yeah. I think this will work. We will have to make a dictionary for everything though. So it is going to be O of n times the length of the pattern, m being the length of the pattern. But we also will, if we really think about space efficiency, we can deallocate the dictionary after every turn because we don't need it anymore. So it would only be O(n) plus m if we did that, because we need 1 for the word list and then 1 dictionary for the map of each word as we're doing it. Okay, let's go ahead and try implementing this. Let's make that pre-processing a separate function. Map is a reserved word. Character map for letter, for character in word. Oh yeah, and result is going to be something. Character is in the character map. As a matter of fact, we don't need a map. The keys are going to be the characters, and then the values are just going to be 0, 1, 2, 3. So really, we just need some sort of linear data structure, such as a string. But then we would need to know what index it is at, which may not be the most efficient way to look it up. All right, let's just do dictionary, why not? We can think about that optimization a little bit later. So if C is in the C map, yes, but the point is if it's not, then it is going to be that. And if it is in it, then, oh yeah, length C map, and then result plus equals C map C. But either way, we want the result to be plus equals C map C. So actually, if C is not in the C map, add it, and then afterwards, either way, get it from the C map. All right, and then we we return. Okay, now for word in words, we want to have a processed list, and then what we do is process it, and then processed append, pre-process the word. Pattern is going to be pre-process the pattern, and then for word in words, I just had a realization. We do not need to go through this twice. We only need to go through this once, and we don't need to store this. We just need to process. The word is going to be, we're going to pre-process the pattern first, right? And then we're just going to go through the words. We're going to process each word, and then right there we're going to compare. Rename this so that we can actually use the word to return it. Processed word is going to be, yep, and then we go if processed word is equal to the pattern, then we're going to have a result, and we're going to append it to the pattern, or we're going to append the word to the result. Result append processed word. Okay, why are we calling this processed word? We can just call it processed. Sheesh. Okay, and then we return the result. Right. Why wrong answer? Oh yes. No. I literally said append the word to the result, not the processed word. Yeah, there we go. Okay. Now let's see how efficient it actually is. Okay, we have a problem. Why does this not work? Let's see. So this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 0. And then this would be 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 0. That's why. That is why. Do you know why? Because I failed to think about when we go over 9. I was like, oh yeah, number per letter. But there's only 10 numbers, and there are 26 letters. So we can map them to letters instead. To do this, we need a list of the alphabet. Do we need a list of the alphabet? Or can we do the ASCII keys? I was going to say we need a list of the alphabet, and then we can use this to look up the index, like get the alphabet based on that. But we can also use it to convert to ASCII. Okay, how do we convert to ASCII? Okay, sometimes I feel like I talk, or my brain goes faster than I talk, and then my talking makes 0 sense. So let me know if I should slow down and explain myself more. Ord. Character to integer, integer to character. Char of that. Okay, so yeah, we don't even care really. We just want some sort of character. So let's just go char like this. And let's see. Let's go. All right. Runtime is amazing. Memory is pretty good as well. All right. So it looks like we found a pretty good solution. This has been the fastest LeetCode with me session I've done so far. Normally we do 2 problems and they take me like an hour to do. So I'm feeling pretty happy about this. But yeah, that's a wrap for today's LeetCode session. As always, let me know how you would have solved these down in the comments. And if you're new here, I'm a computer science student sharing my journey to becoming a software engineer here on this channel. So if that sounds interesting, feel free to stick around, and thanks for watching.